All right, class. So picking up where we left off, this is our quote unquote Friday lecture, but principle, you guys can just watch these back to back or on your own convenience. So I'm not going to provide a review. But what we're doing now is just picking up with the Streeter-Phelps model that we were developing for predicting the dissolved oxygen concentration within a stream. This is where we left off last time. We said that in the plug flow part of the stream, there's a reaction component and then reaeration. So we described the reaction component. And now we need to describe the reaeration. So how quickly is oxygen transferred into the water? This is the question that we're trying to answer. We know at an equilibrium what the Henry's law constant predicts, but this does not necessarily tell us how quickly oxygen gets into the water. In order to quantify how quickly oxygen partitions back into the water, we look at what's called the oxygen deficit. The oxygen deficit is the difference between the saturation value and the actual dissolved oxygen concentration at a given point. So at any given point in the river, let's say d sub x, the oxygen deficit d sub x is equal to saturated dissolved oxygen concentration minus dissolved oxygen concentration at point x. Another quantity that we need to define is the initial oxygen deficit after mixing. We call this dA, and dA is equal to dO sat minus dO x equals 0. In our above labels, we also called this dO mix. Essentially, this was the point where the waste enters the stream and is mixed. Now, this rate is going to be proportional to the oxygen deficit. So the rate of reaeration is proportional to d sub a. Therefore, the larger the DO gradient, meaning deficit, the larger, the faster the rate of reaeration. Now remember, we talked about pretty early on that turbulence can affect reaeration. So if the water is somehow more turbid, or not turbid, but if there's a lot more mixing, it can also influence. So mathematically, this rate works out to be the rate constant, Kr, times the oxygen deficit. Here, Kr is the reaeration rate constant, which I already defined that. So Kr is the reaeration rate constant. Again, DO sat is the saturated dissolved oxygen concentration. and DO is the actual dissolved oxygen concentration in the water. Actually, this should be the initial oxygen deficit. All right, so if we put this all together, what we have is the advection of a plug of water going from the mixing zone down the stream. We also have reoxygenation, reaeration, then we also have deoxygenation. So there's these three terms. And if you put them all together mathematically, you can show that the oxygen deficit is a function of time is equal to this entire equation. Now this one is pretty important for you guys, so you want to make sure you have this bookmarked or highlighted. You know where it is and how to use it. This is what we've been working towards here for the last lecture. All of the terms are defined in here, and so I'm not going to go through those in detail, but it's important to kind of recognize what this curve does and what it looks like. And actually what I did last year is I did some demonstration of how you could plot this curve. So I'll give that to you guys as a suggestion. Go ahead and take your favorite program. You could use Excel, probably easiest for this, and just create a few different columns for time. You can use distance if you want to also see how the velocity of the water flowing down the stream influences this. And then calculate d sub t. You'll get a nice qualitative picture of how this equation works. And what you can start to do is adjust variables like K sub D, the utilization rate constant, or the reaeration rate constant. You can adjust the initial BOD and see how this influences things. And that, you should be able to make some predictions, right? If I slow down the oxygen utilization rate constant, what's going to happen to the oxygen sag curve? And if I increase the reaeration rate constant, how that's going to affect things. So I encourage you guys to do that, and it'll be pretty useful. I thought I actually had some graphs here, but. All right. So a second derivation of this oxygen sag curve, and actually, by the way, just so we're all on the same page, this is called the Streeter-Phelps equation. So another way to derive this equation is to consider plug flow, but also have it be dispersed. So dispersion is kind of analogous to diffusion within the stream, but actually happens faster. So in this approach, we're going to consider an equation that is the advection dispersion equation. Now, if you do more classes in environmental engineering, you're going to see various forms of this. It's very important for our field of study. It relates the change in concentration with change in time to what's called a dispersion coefficient. It's the partial derivative of c with respect to distance. the velocity of the stream. This part describes advection. Advection is just movement of the parcel of water downstream. Now, if this were all that was occurring, not much would happen, but there's also reactions. We'll just make it general and sum up the different reactions that can happen. This will include oxygen consumption and reaeration. All right, so you don't have to know this equation necessarily, but it's the starting point for what we're going to do. What we're going to do is ignore the contribution of dispersion in the system, and doing that is essentially saying that we have a plug flow system. Dispersion is kind of that phenomena that I told you guys about a while ago, where if you have some mixing or non-linear velocity distribution profile within the plug flow reactor, you're going to have actually some level of mixing of molecules throughout that non-ideal PFR. So we don't have time in this class to go into that in too much detail, but it's really interesting if you study in additional classes. So we're going to ignore the contribution of dispersion and also assume steady state. Conditions. So what that will result in is dc dt within a single parcel being 0. And then we also cancel out that dispersion part. So we're then left with dx dc dx plus the sum of reactions. What we'll notice is that C is no longer a function of t. So that allows us to remove the partial derivative. And what we get is dx dc dx is equal to sum of reactions. And then what we're going to do is replace C, which is the concentration of oxygen, with the oxygen deficit. When we do that, we get dx dd dx is equal to kd L minus krd. So the last thing we want to do is, at least in order to get it similar to the equation that we had before, is we want to do a variable substitution. So this is our differential equation. But we can also have it in terms of t. So the velocity is going to be given by x over t, which gives us dv dt is equal to kd L minus krd. All right, so I'm going to trust that, even if it's been a while since you took differential equations, you could create, a solution for this. I'd encourage you guys to think about how you might do that. I'm not going to ask you specifically to do that math. You've seen it before, but this is where it comes from. This is the differential equation that we're solving. We have certain boundary conditions. Those are important to recognize. At time 0, D is equal to the initial oxygen deficit, dA, and L is equal to the initial BOD. That is the point right after mixing. And then at time t, D is equal to D sub t, and L is equal to L of x equals t. If we apply those boundary conditions, we end up getting the same equation. All right, now, the learning objectives, right? I don't expect you guys to like regurgitate some sort of derivation for this, but what I do expect is that you can calculate things based on this equation. You could understand what the equation does. You could see how that equation models the oxygen deficit within a stream. Those are the expectations that I have for you guys. So we're not really focusing on the mathematics in this course. Now, when I plot this, this is what I get. It looks something like we would predict based on the picture that we've been drawing. So there's a few points sort of interest here. This is right where the waste mixes, so label that. So it's a little bit, in terms of the picture, it's a little bit off here, but if you look at the distance, it's a 0. And the difference between the DO at x equals 0 and the saturated value is the initial oxygen deficit, which here I've labeled as DO, but you could also call it DA. An important point is this minimum value. We're going to talk about that in just a second. But the DO minimum is going to occur at a certain distance. And this is where we have the critical oxygen deficit as well. And this is kind of a key point for us. You can almost think of it as a design parameter. We need to know at what distance the critical point is going to be. Which leads us into our next problem. Find the critical point. So to find the critical point, all that we do is take the derivative of our expression for D. We evaluate it at we find where the derivative is equal to 0, sorry. And if we solve for the critical point, what we end up getting, actually, I wrote out here. All right, so conceptually, I don't think I need to hammer this home, but our critical point here is where the slope is no longer changing. So we could take the derivative if we want to, solve algebraically for the critical point, but I'll just tell you this is what we get. And again, this isn't a math class, so I'm not asking you to do the derivative in the algebra, but I do expect you to know how to use this equation to find the critical point. Now again, why is the critical point actually important in context of this concept? It's important because it tells us the point at which the lowest steady state DO concentration would be. We can solve this value mathematically with some pretty good accuracy. And so when designing a certain treatment plan or when figuring out how the BOD5 is going to affect the critical point is sort of a key objective of the Streeter-Phelps equation. In other words, it defines the worst case scenario in terms of the oxygen deficit. All right, so I'm going to leave it there. We do have 2 additional problems. I'd like you guys to sort of think about these and work on them on your own. The first one is kind of a qualitative question, and the second one actually has you do some calculations. Last year, I had students submit this in class. So what I'm going to do is just provide the solution on the written notes. If you want to email me your solution, you can do that. I can tell you if it's right or wrong. But in any case, I'll post the notes here within the next few days. All right, take care.